Okay, so let's talk about element of chance. In this section, we're going to look at what is element of chance and how we're going to deal with few things that we use calculus to calculate before. And right now, we're going to give you an alternative solution for kind of approximate the values that we had by using calculus. All right, so the first thing is, well, what are the disadvantages if we're using a computer simulation? So these are a few of them that are listed here, that you should be aware of. Okay, so the few things here is, well, we have a lot of advantages. We can predict things, right? And obviously, but sometimes the simulations may be expensive in time and money and to develop and all that, right? So if you have a software, of course we have Vensim right now, but there are certain things that you cannot use particular software to build or the calculate or the simulate. The best example I can give you is a flight simulation, right? So if you want to become a pilot, maybe you need practice, right? So each time when you practice, well, the one option you have is you actually operate a real flight. But if you operate the real flight, you cannot recreate all the circumstances. What will happen in the sky, uh, how the air pockets affect your flight path and how you handle those, maybe the high wind kind of things, right? So one thing you can do is, of course, I can build a simulation and make a lot of people use it so they can practice with those parameters built in to the system, and then you just get the feeling of the flying a plane, but you're not in actual plane, right? In the both situations, like for example, even if you're flying an actual plane, yeah, you cannot create these circumstances, but if you're doing in a simulation, you can. So that is the advantage. But what is the disadvantage is, of course, you have to build the system, you have to program it, you have to get some people to work on it, so you spend some money to develop it and it takes time. So that is the bad part. But well, I wouldn't say it really bad, because after you develop it, a lot of people can use it, right? And so that is one example. Okay, so the others are, right, yeah, it is impossible to get the accurate test as it's exactly going to happen this way. You cannot say that, right? So that is the other problem. This is just an estimation. It's never going to be exactly, you cannot say 100% accurate, right? There are some flaws, right, because of the assumptions and the parameters you are applying, and the results may be difficult to verify. Of course, we don't know the phenomenon really happened before or not, so situation is based on data, right? So because of that, yeah, we cannot verify it is really going to happen in this way, right? Right. So we cannot sure we understand what the simulation is actually does. Yeah, well, it doesn't have the artificial intelligence for sure. It will behave, the simulation will behave uh, depending on the data you give in, right? And then whatever we written, right? Especially we are talking about random numbers today. Is that exist? We will talk about that. There's no such a thing called randomness. So in that case, yeah, we will face some situations, especially in the simulation. Okay, and then when the simulation is probabilistic, so that means it can be happen, cannot. So there is always element of chance involving, right? We have to be careful on making the conclusions in that case, right? Right. For example, there's a probability of the corona will kill, I mean, the COVID-19 might result over 100,000 deaths, right? So that is just a probability given you by the model that they were using, right? So there is a, so you come up with the conclusion. It can be true, it can be false, whatever, right? So in that, like that, so there is a probabilistic results you always get when you're making a conclusion out of it. So those are things, actually disadvantages that we consider in the simulation, because it's not going to give you a right exact result. It's depending on a lot of things, right? Okay, so saying that, let's move to element of chance. When we're talking about element of chance, so this is actually depending on the random numbers or the pseudo generated numbers when it comes to the computers, right? But well, to get the idea of it, I will talk about something like dart throwing. Okay, so before I go into this, what is Monte Carlo simulation? Well, it was introduced by John von Neumann, in the era of World War II. Actually, he was introduced this model to estimate something related to atomic bomb, actually. So it is like, if you read about his biography, it is listed there. Especially if you want to build the shields, which is called the constructor dampers of the shield for the atomic bomb. So the experiment is very expensive. You cannot blow up the bombs all the time to do this. So they really doesn't have the good knowledge how the neutrons are working, how it behaves by that time. So to do the experiment properly without doing actual things on the field, this von Neumann introduced this technique, right? So there's a little bit about von Neumann. I think he's the smartest guy, the biography I have seen among all the people or the legends on the physics and everything that you're talking about, like Isaac Newton, Einstein. If you come to that, I think von Neumann is on the top. Okay, the reason for that is, yes, he learned calculus and he was able to understand it by age 8, right? And that's a big thing, right? And then also he can remember one column of telephone numbers by just glance, right? I mean, by just looking at it once, and he can remember it. So that's pretty interesting. And then he also contributed so many things to many fields, not only computer science. If you're talking about economics, right? Nuclear weapons, of course, I'm not. And then quantum theory is the most interests me, right? So the quantum theory, logic, and then all those fields he was contributed. So he earned his PhD in age 22. So that is one significant point. All right. So enough about von Neumann. So in Monte Carlo simulation, we actually calculate the probability. Based on probability, we calculate that, right? So before that, let me introduce what we learned so far, right? So this is a graph, and if I want to get the area, so of this area right here, how do I calculate that? Well, I'm going to divide this to little pieces, right? Remember that we did it in calculus, right? So introduction to calculus, we were talking about what is calculus and how we're going to use that to calculate this, right? So how we did is we just break this to little pieces, right? And we get the one square and then the area of the other square, I mean the rectangle, and then the rectangle of each, and then we calculate, we add all together and calculate the area. So that's what we did actually, right? Why we need the area? Well, if you say velocity is what? Distance over time, right? So if this is if this is just a timeline and then the velocity, right? So in that case the traveling distance will be equal to nothing but t, right? If this is t and if it is v in that case, right? So this means what? So the area is the area is equivalent to the distance you traveled, right? So that's what we did, and then we break this one to very small numbers, right? The very small numbers, so that is what the limit is about, right? Breaking into pieces like that. Okay, so that is if you know calculus. So if you don't know calculus, and there are some other methods to calculate this, so that is what the Monte Carlo is introduced. So that's what we're going to look at. Okay, so that is the entrance or the introduction to what we're going to do today, right? Okay, so yeah, this is what we look at right earlier when we having something look like this, which is this is antiderivative of a function, right? So this function from a range from 0 to 2, and then you write it in this form, right? So this is the calculus. This, if you do this, it will give you the whole area which is covered by this graph. All right, so yeah, in order to do that you have to know how to solve this equation. So if you don't know how to solve this equation, well, the Monte Carlo introduced a new way to do this, right? So this is what he did. So it's pretty cool. I mean the simulation, right? Right, so what we do here, right? So in this case we just divide, get a square, right? So this is a square actually, and in that square you consider that you're throwing darts, like so the small darts, right? So these small darts go and hit on the board. So that's what you do, right? Yeah, and it can hit anywhere in this. So that means if you aim it 100%, it can go and throw it anywhere and it hits there, right? So that is a random movement. So this is a random movement. So you randomly throw it into this board, right? And then what you do is you consider how many will hit below this graph, right? And how many you have above this graph, right? So you have to keep in mind in two things actually. The two things will enough to calculate the three things. What means the total number of darts you throw, total number, right? And how many hit above or the below, right? So in that case, if it is above, if I know the above and the total number, right? I know this, the rest is what? Rest is below, right? So that means total number minus above dots, right? That's equal to the number of dots below the graph, right? So that is something that we know. Okay, right? So so that means if I know two things, I can calculate all three things, right? And using this, I can actually approximate the area below the graph. So that is what the Monte Carlo simulation is all about. So how are we going to do this? Let's look at an example, and then you can have a clear idea what this means, right? So so it says here the estimated desired area we take, right? So that's the area is equal to number of darts below, right, divided by the number of darts. So that is the total number of darts, right? Is the number of darts, and the number of darts that you have below the graph is this much, and you multiply that by the area of enclosing rectangle. So this is the whole area of rectangle, and that is easy to calculate. It is 1.5 into 2 in this case, and then you know how many total dots, that means how many times you throw your dot, right? And then you get how many is hitting below this graph, right? So you can count it, and then you mark it down, right? So this is an example of it. So right here, the above square, so this has a 2 in this from here to here, right? And then above is 1.5, right? So you multiply those two, you get the area of this square, right? Total. So that is 3 right here. And then if I throw 1000 dots, so yeah, I'm throwing 1000 times, and then I get how many hit below. So I have this much, right? So I know this, I know this, and I know this. So what do you do, right? So you can calculate the area. So the area is what? Area is nothing but I'm taking this value, which is the number of dots hits above is this much, right? And that is out of what? 1000, right? Okay, and then you multiply that by my rectangle, which is number 3. Right. So if you do this, this is actually equal to this value right here, right? Well, it's talking about what is the percentage of falling this number below the graph. So if you have a graph like this, what is the percentage of this? If it is 1000, it is 778. Then you're asking what is, if it is 100, how much it is. So what you do is you use 778 divided by 1000 multiply by 100. So that is 77.8%. So that means if you throw 100 dots, 77.8 will fall below the graph per 100. So that's what it says here, right? So percentage is always out of 100. So how do you calculate that? Well, if you get the total number and how many you hit, so this means, right? So let me recall this one more time. So I mean, you calculate the area, that part is done, right? So let me talk about this little line right here a minute. What there implies here is, if I say, okay, so the 1000, this is how you calculate, how to calculate percentages, right? Percentages, right? So first you say 1000 dots, if 1000 dots, right? If 1000 dots, then how many number of dots below the graph, right, will be equal to what? 778, right? Then if one dot, then the number of dots below the graph will be what? So to get 1 here, you have to divide this part by 1000. So in this case, I have to divide the other side by 1000 as well, right? So that's how we get that. And then what do you do? And then we'll say if it is 100, right? Then what happens, right? How many below that? So if it is 1, if you want to convert 1 to 100, what you do is you multiply this side by 100. So in that case, you have to multiply the other side by 100 as well. So it is 1000 here, multiplied by 100. So this 20 to 20 cancel out. This is 778 divided by 10. So you usually get 77.8. So you put it as a percentage like that. So this is how you calculate the percentages of anything, any out there. If you want to calculate the percentage, follow these 3 steps. You can calculate the percentage of anything. Okay, right, so that is something extra. Well, it's talking about here, so that's why I pointed out. But anyway, so how to calculate the area is you just get the area, multiply by 778 divided by 1000, which means number of darts below the graph divided by the total number of darts you throw, right? Alright, so I can ask one extra question here. What is, how many darts hits above the graph? So what is that? That will be equal to 1000 minus 778. This is how much it will hit if your graph is like this area right here. Right, so that means you know how to calculate either one, right? Okay, so keep that in mind as well. Right, so if I ask you how many hit above the graph, so obviously it will be the difference of these two, right? Okay, so that is few more things than what you see here, right? I hope you understand that, right? So this is a review question. So this review question, we have a graph which is not a curvy graph. This is just a one line, right? So this, you can notice this will be equal to y equals mx plus b type, right? So that is the graph type, right? So we already know this is a line, right? So what does this line look like? Well, let me draw it here so you can see properly, I guess. So if I have it like this, where does this cut the y-axis? Well, if I put 0 here, so the y value will be what? 1, right? So it will be go somewhere here. So it is 1, number 1, right? And of course it will be go somewhere like this, right? So that is your graph, right? And I'm taking the values from 1 to, so my one of my x values are here. That is my starting point, and then I'm taking it up to 5, which is somewhere here. So that is my area. So this is the area of my graph that I'm going to calculate the area of this one right here, right? So the first thing is asking what is the smallest rectangle that you can draw here which has the highest height. So the smallest rectangle will be somewhere here, right? So if I take this value and bring it to here, like this, right? So this is what you get, right? This is the rectangle I'm talking about. There's a range from 1 to 5. And what is the highest value? Well, the highest value hit when it is 5, right? Yeah. So when it is hit 5, what is the highest value I get? Well, that is, I'm going to apply x. This is my x values, right? X bar. So if I apply 5 into this is what I get. So that means the gx will be equal to 3 multiplied by 5 plus 1, right? So the 1 is there, and then this is also 16. So that's how you calculate 16 here, right? So that is just a rectangle, and then I'm just taking the calculating the maximum height that I can get. Right, so this, then what you do here is, suppose the random number, the random hit the simulated darts, so that means somebody throwing some darts, just think like that, okay, at the location 3 8. So what is the 3 8 means? Well, that means in x direction it is 3, and y direction it's, I mean 3 11, I'm sorry, so the y direction it is 11 somewhere here, right? So it's asking whether is it below or the above the graph. Well, I really don't know. So how do I calculate this? Well, you have to apply what is the value actually at this point, right? So what is the y value of this point? That's what I had to calculate. So how do I find the y value of this point? Well, I can say this is my equation, right? Okay, and then for x I'm putting 3. This is this value right here, and then plus 1. So what I get 10, right? Yeah. And it says, okay, so the dart hits what? So the dart hits at 11. So but I know this point is 10, right? This is 10. So obviously whatever it hits above the graph, right? So that's how we figure it out, that it is above the graph. So that is what the answer is, above, because of this, right? Okay. All right, so let's move to the next question. It's asking about let me pull it out up to here. Right. So what is the next question is asking is, using a geometry, compute the area under G. Area under G, right? So what is the area under G? So let me draw this. So now this is my graph again. Okay, and then I have from 1 to 5, right? Then I have this little thing like this, and it comes down here, right? Okay, so well, it's asking what is the actual area on this part right here, right? Without darts drawing. I mean, how do you calculate this? Well, I know this equation is this, right, plus 1, right? And then here it is 16, I know that, right? What is here? What is the value here? Well, how do you calculate that? Well, the value here will be what? When x is 1, right, this is 3, and it will be 4, right? So right here it is 4, and this is where it's 16. Okay, so one way of doing this, of course, it is trapezoid, right? So you can calculate it like that. So if you don't know how to calculate it using a trapezoid area formula, there's another way of doing this. So I would draw a line from here to here, and then calculate this area. What is that area is equal to? What is this area equal to? Well, that area will be 4 multiplied by, right? So what is the value from here to here? Is 4, right? Why? Because it's not starting from 0. This is 5, so it is 5 minus 1. So it is 5 minus 1 is the area from here to here. Right. So the value is what? 16 right there, right? Okay. So now I have to calculate this area. How much is this area? Right. So what is this area? Well, that area will be nothing but the height from here to here, which is, so this is plus, height from here to here is nothing but 16 minus 4, right? And multiply by the value from here to here, which is 4, and divide this by 2. So that is the area of a triangle, right? Which is, you can imagine there's a square here. If I have a rectangle, that will be 4 into 8, and then 4 into 12, and then you cut it half, that will be divided by 2, right? So that is what it is. So anyway, so when you calculate this, what you get, right? So here it is 16 as is. This is 12 multiplied by 4 divided by 2 is 24, right? So this will be equal to what? Well, that is 40, right? Okay, so that is the one way of calculating. Oh, you can do it like this as well. So what is this one does is, well, this distance is 4, you add this to this, and you multiply that and divide by 2. So what is it? What is means the trapezoid area is equal to the minimum height plus the maximum height multiplied by distance from here to here, right? So this is the maximum height, minimum height multiplied by the distance from here to here, which is 4, and divide by 2, right? So that is the same thing. So you get 40 anyway. right? So that is how you calculate. So keep in mind, when you're asking the area under G, it doesn't mean that you consider this area as well, because I'm taking the range from 1 to 5. Okay, so that is the area that they're talking about. Okay, right. So then the other question is asking here to compute the area of the smallest enclosing rectangle. Well, the rectangle means I have to just have a little dots like this. So this is a rectangle I'm talking about. That's easy, right? So if you draw it like that, so this is a 16 and this is 4, right? So you know this is 16 multiplied by 4, which gives you 16 times 2 is 32, 32 times 2 is 64. Right, so yeah, so that's the value, right? Okay, right. So then it's come a little bit difficult. I mean, well, interesting. I would say interesting. It's not difficult, right? Okay. So how do I calculate? Solve this problem. Suppose the simulation throws million darts. So the million darts you're going to throw at the rectangle, although any value is possible, of course. Yeah, so when you throw it, indicate the most likely percentage of the darts landing below the graph, right? Okay, so how do I nail this problem, right? Suppose that you throw million darts, right? A million darts at the rectangle, right? So this is what actually confusing you for this question, right? Although any value is possible from the throwing, the choice indicates most likely the percentage of darts landing below the graph. So it's asking the percentage, right? It's asking the percentage. So what is percentage means? Percentage means out of 100, how much is going to be. So that's what actually the percentage means, right? So instead of million, what if it is 100? How many it's going to be? That's what they're asking, right? So the good way of doing this is you know the area using the Monte Carlo simulation. We know this is equal to the area of your rectangle multiplied by, right, the darts below, right? So the darts below divided by what? So if I want to calculate for 100, actually I just put 100 here, right? So this is what it is for the 100. Okay, and so what is this equal to? Well, I know the area of my rectangle, I mean the below the dot, without calculating any of this. I know it is 40, right? Yeah, we calculate it up there. And then what is this area? It's right here, which is 64, right? And then I don't know this value, which is, let's call it x, and I know 100 is here, right? So what is this equal to? Well, this is equal to nothing but, you say 40. I'm taking the 64 this side, so it is 64 down, and then I'm taking 100 up there, so it is multiplied by 100 is equal to x. So this is the percentage actually, because for the 100 darts, how many it will hit? So this is actually equivalent to 62, and you put a percent because I just calculate for 100, right? So that's the percentage. That's what it means. Yeah, so this is the actual calculation for the percentages. So if you, instead of you say 1000 darts, if you want to calculate the percentage, it's just using 100, right? Okay, so this is the answer for that, right? Okay, so the other one is asking if 600 of a million darts. So this is where the million comes in actually. This is just deceiving. I mean, if you're looking at this one, right? Darts lands below the graph, estimate the area. So okay, so that is very straightforward, right? In this case, has nothing to do with this. So we always going to use this equation, which is area is going to equal to so in this case this square is 64, and you multiply that by number of darts below, which is 600,000, divided by 1 million, right? So you just cancel out all this to all this, and then I have 10 below. You multiply you multiply this to this, which gives you 384 divided by 10. It gives you 38.4. Right, so that's the answer for that. Okay, so that's how we calculate it. Right, so now you know Monte Carlo simulation, what is the idea behind it, and how you do the calculations. Right, I think it's clear enough to answer any questions related to this. Okay, right. So let's move the measure quality. All right, so this is something very important, the standard deviation. I will talk about that in a minute. Right, the measure quality is something, well, we talk about just drawing dots. It's not going to give you accurate data, right? But it's a randomness, of course. And so you calculate the average values. You can, if you want to really measure it and get the accurate data, what do? Well, you do this several times, not once, right? Well, I just talk about throwing darts and all that. It's just a physical activity, but it is not actually. When you're doing this in a computer, obviously you can throw some random numbers. So that's what you're actually doing here, right? So some random numbers you throwing into, that's what throwing dart means, right? So just use some random numbers and then populate that and see how many is below, how many above, right? So that's what you do. When it says I want to calculate the accurate data out of this, right? You can do this several times. Like for example, I do this simulation 10 times. So actually that means what? I'm throwing 10 million darts, right? Each time million, and then calculate the area I get below the graph. So that means, yeah, there's a lot of calculations, right? Yeah. What I'm saying is, well, you get your board here, and this is your graph, and then I'm just drawing these values in there, and this is a million times I did that, right? And then I calculate the area, and then again I'm doing the same thing for the same graph, and doing this a million times again, and then I calculate it again. I'm coming there, do the same, right? So what do you get? Do you get exact same number each time? No, right? So you get different numbers. Why? This is a random simulation, right? Okay, so when you do this so many times, you get different values for your area, right? Okay, to improve this measure quality of this to area, we get from here I get one area value, from here I get another value which is from here, and so on. I get some area values there, right? So the good way of measure your quality better, what you do is you get the average of this. You get the average of this, but average of this means the mean of the values, but you can get it more accurate values by using a standard deviation. So I will do one example of what is standard deviation. Even the book does not explain that over there, so I will talk about this later in this lesson, right? Yeah, so if you calculate the standard deviation, you get much more closer value to the accurate. So that's what the measure quality, when you calculate the measure quality, that helps a lot. Okay, right. So the next section on this book is talking about a little bit on simulation development. So this is actually based on this is actually advice on the developers, the computer science people, how they should manipulate this, but that is also applied to your project as well, and what you do in your project, how you do the modeling. So that's also related. So that's why I'm just pointing out both here, so you can have a good idea about what we are actually doing as our project, right? And how we come approach to our project. So this is what they are just suggesting is with the dynamic modeling. The first step is you should not, you don't do the coding actually if you're a computer scientist. And if you're just modeling using Vensim, of course you're not going to jump into the Vensim and doing it, right? So there are some steps you have to follow. These are things I want you to put it in your project as well. Analyzing a problem is the first thing. I already asked you to do that on your report proposals, right? Yeah, so what you do in that is you introduce your problem and then you analyze your problem and things like that. Again, of course, you have to analyze the solutions after you get it out from the Vensim. But the problem scope is this part, talking about the problem. And then formulating the simulation model on a paper, considering the data. Yes, you collect the statistic data, and so you formulate it. You finding the rates, change of rate and things like that. Change of rate is what? The change is delta, whatever the value, divided by delta t over time, how much is changed. Or you can say dq over dt, it's the same thing, right? So this is what the rate of change means, right? Okay, by the time how much it changes. So I think you have a clear idea what is rate of change by now, right? Okay, and then SCM, you're making assumptions to simplify your issue, right? And in this case, in this population growth, things like that, migration, immigration, and then the deaths caused by accidents you ignored, right? And then you calculate things. Determine the variables and the units. So the units and the variables is important. If you're using centimeters, meters, and things like that, it's a different calculation, or the kilometers in this case, than the yards, right? The miles and things like that, right? It's a different unit. So in this case, you cannot mix these two. Well, in the history, there are so many messed up things happened when they're mixing up these things. You know already, right? Millions of dollars losses. There are losses of those things because of the time, also the time waste on the experiments, because well, some measurements are wrong, like calculating different units, right? So you have to be careful on that, right? And then establish a relationship among the variables and the submodels. Submodels in case, yeah, we know in even in malaria we just divide the mosquitoes and the human, and then again the submodels of human, infected, recovered, and the host, right? And then things like that. And then also for the mosquitoes, we consider the infected mosquitoes and uninfected mosquitoes, so kind of things like that, right? And determine the equations. Of course, you can divide the equations into pieces, right? And then break the problem into small tasks and write it. So that is the same thing that you do in your model report. I mean the final report, right, on your given model. In this case, it's the same for the developers who develop the system. So that's why they're talking about this in this chapter as well. Okay, so right, so let's move forward and look at a few more things here. When you're talking about modeling, I mean the computer science part, that's a pretty interesting thing they're talking about here. So what is debugging, right? So that's what I just put it out there for people who are interested in computer science, programming, and things like that as well. How this came up? Well, as I said, all the computers made of switches, right? So they have switches which is on and off, right? Zeros and ones. Early days we did not have a little small circuits, so we had light bulbs actually. Light bulbs plug into these switches, right? And you turn on and off these things and calculate the values. So that's what the computer looked like, right? So this is a big huge room long ago. Why? Well, we don't have a little circuit to do this, right? Okay, right. In this case, yeah, the light's getting really hot. Because of that, you had some windows open in your building. So these are the windows that's left open in your building, right? So these are opened, right? Just to flow the air and stuff like that when you're working on it. So this is a huge building and has a computer in it, and they had some lights, switches like that in order to make it electrically work, right? So somehow because you have the open windows, there are bugs went in there. So there's one bug which is went and fried the circuit. So the switch circuit was burned because of them, right? So there's a bug here, and he burned this thing, right? So yeah, after that, all the calculations, whatever this lights showing you, one of the lights always off, right? So all the calculations are messed up in this case, right? So that's what happened, and then they figure out, oh, the answers are wrong, and then so they went in and then looked for it, and then they found there's a bug, right? So taking off the bug is we call debug, right? So if you have a problem in your computer or anything like that, we call there's a bug in my program, right? So the bug and debug comes into the action because of this. Already this bug is also still there in the museum, the National Museum. So they have this bug still in there. I never go and see. I just Google it and I saw the pictures of it, right? So so that's what happened actually, right? Okay, so so that is about bugs and debugging, the concept, right? So that's how the concept came into the topics. All right, so standard deviation. So to make the measure quality better, you do the calculations of standard deviation. You do this several times, the simulation, and you calculate it. So in this case, consider the values. Yeah, we have, let's say we have few values. These are actually, I took it from some website. They're measuring the dog heights in this one, right? Okay, and right, so it doesn't matter what is the value is related to. I just want to calculate the standard deviation. So what you do is you add all these values. You add all these values and you calculate the mean. So mean is what? Just adding the values, and number of values I have is 1, 2, 3, 4, and 5, right? So I divide it by 5, I get the mean. And the variance is nothing but I take this mean and I subtract from each. So here I'm subtracting it, here I'm subtracting it, right? Here I'm subtracting the same value, and here as well, and from here as well, right? So the funny thing is, when you do that, of course you will have negative values on some, right? So this one is negative, this one is negative, the others are positive, of course, because this number is larger than this. Right, so I don't want to deal with these negatives and positives. Because of that, I'm squaring it. So you can see I'm squaring the value, right? I'm squaring the value, squaring the value, and squaring the value, right? And then I'm just dividing it by the total number again, which is 5. So I get some value for this. So that is a variance. We call this a variance, right? And yeah, since I square it to get rid of this negative value, I have to get the square root of that as well. So then I'm just getting the square root of this value, and I call it standard deviation. So the standard deviation is nothing but you calculate the mean, you subtract that by each value, and then you square it, add it, and then divide by the total, and then you get the square root of it, right? So that is what, that's just a simple explanation what is standard deviation is. Okay, right? So then let's move to the random values. What is random and how that makes sense, right? So this is actually the last part of this lecture. What is actually random numbers? Okay, well, it's very hard to say what is random. Is that random exists? This is the one question, right? Well, random means it has to happen without a sequence, right? Obviously you cannot go and create something and call it random, right? You had to have it has to happen without any formulated the phenomenon. For example, let's say calculating, I just want to get some random number, which is, it should give me, first time it should give me 5, next time it should give me some value like 9, sometimes 6, 3, right? So if I get random numbers from 1 to 10, I can pick any number by just thinking of it, right? So the thinking abilities only human has in mathematics, right? If you get to terms of mathematics, the humans are the only one who has it, right? Because of the others don't learn math anyway, right? So these numbers are just belongs to us. Well, we are just come up with our mind. There's no equation for this. It's just a thought. So you cannot give the thought to the computer. So in that case, how do computer generate this? Well, that's a big problem. We don't know how to calculate it throughout the computer, right? We have to come up with some system to do this. Well, one of the things that you can go with the timestamp, because the time is changing all the time, so you may have a little chance on that, right, using a timestamp to generate random numbers. So here, one of the things that they're introducing as a linear congressional method, right? So in this case, you just throw a seed. Well, it says seed is 10 in this case, right? And what does this means here? Well, what is I'm doing here is I'm getting some number called multiplier, right? And then I'm calculating the previous R value just before this one and add 1 to that, and then I'm get the modulus of 11, right? In this case, this is an example of it, right? Okay, so what is this actually? Okay, let's say I have R0 as 10 and I want to calculate R1. So what is the calculation for this? Well, 7 times, right? 7 times R1 is this, R1 minus 1 is R0, which is this one. So this is 10 plus 1, right? Modulus means I'm dividing this by 11, right? And get the remainder, right? So that is what the modulus is. It's usually like this. So this is a modulus. So this means what? In this case it's 11. So what I get here is 71 mod 11. So how many 11s are there for the 71? Well, as is 66 is the closest it goes, right? And then from 66 to 71 there's 5 remains, right? So the R1 value is 5. So that's the first value it give you if you do this, right? So the next time if I want to calculate R2, right, R2 will be 7 times, right, Rn minus 1, which is now it is R1, which is 5, right? There's one step ahead, below, I mean one step before, right? Plus 1 and the mod 11, right? Mod 11. So what I get here? Well, I get 36, right? 36 mod 11. So that will be equal to 3, right? Yeah. 36, 33 is the closest, the 11 times 3 goes to, so then the 3 remains. So that's what it is. So that is R2. So the R3 again, if you calculate like that, I get here I get 21, 22, 22 mod 11 is 0, right? Yeah. Okay, so like that. So I get random numbers according to this is nothing but 5, right? The 10 is the first number. Yeah, you can take it as a 10, 5, 3 and 0. So those are the numbers you get, right? So this is the positive integers, of course, you can get. Right, so that is the example showing here. I mean that's how you calculate it, but The one thing I want to point out here is if you're using a mod 11, right, this number never goes beyond number 10. And the lowest number you get is 0. Why? Because I'm taking a mod value, means it's getting a remainder, right? Right, so right here you can see if it is 22, that is already perfectly dividing by this, so that's why I get 0, right? The maximum number it can go is, like, for example, if I had 70, in this case, if I had 75, right, 75, I mean 76, if I have 76 there, right? So 76 mod 11 will give you what? 10, right? Yeah, 66 and then 10 remaining, so it's a remainder. So that's the maximum number you can go. This is the lowest number you can go. So the range is depending on what mod you put it in there, right? Okay, so there's another part on this. Actually, they're talking about in the book that I did not touch because it is actually the function, depending on the function they're just introducing. There's no the concrete calculation on mathematics in that part, but I want to point out the same thing. The questions like this that you should be able to answer. What are the questions? Like, for example, I give you saying, give a formula, right? Write a formula. Let's say write a formula or equation. Write an equation to find random numbers between let's say okay, let's get an easy one. 0 to 20. How do you do this? Well, I can simply say write this equation, I mean, or whatever it is. I can say number is equal to random, right? Just like this, mod 21, right? So what does this means? This means any number I get, and if I mod that by 21, right? So the lowest I get is whatever the number here. So let's say I get 42, right? 42 divided by 22 is what? Exactly 2, right? Yeah, so this is 2, and then the remainder is remainder is what? Remainder is what? Remainder is 0, right? Okay, so that gives me 0, right? And if I have something like 41, what does that means, right? That means if I divide it by this, it is that is actually if I have 41 divided by, let's leave it like this, 22, and then if I have something like this, this is 1, which is 20, and then the remainder will be 20, right? So that's the maximum number you can go. So this is the lowest number, right? So that is solve the problem, right? Okay. So, but what if I have question, the same kind of a question let me get something very interesting here. Not this one. Right here. Let's get some values like between. I want to get from 5 to 20. Yeah. So 5 to 20. So how do I write a function for this? So this is not good for that. Not good for that. So now the number is going to be what? Any numbers give me by. I want to get this range. The first what you do is you get the range from 0 to 15 and then simply add 5, right? Yeah. that will take care of it. So in this case I can get rand, right? And yeah, so what is the value I'm going to mod this by? 0 to 16, 0 to 15. Let's get 0 to 15. How do I get 0 to 15? If I use value of 16, that will give that, right? And then plus 5. So what happens when you do this? Well, let's get some value. So this guy throws some value for me. Let's say he throw me 32. So if he throw 32 divided by 16 is what? 2, right? And the remainder is 0. So the remainder on this case is 0 plus 5. So always the minimum value will be this. Right. Okay, so that solved that part. What if I have the bigger number? Like for example, let's say this guy throwing 31, for example. So mod 16 is what? Well, that is only 116, and then the 15 remains, right? So it is 15 here, the remainder plus 5. That gives you the maximum value to 20. So if I have something like this range that I want to calculate, this equation will solve that problem, right? So that is a range that you can get any range that you want. Okay, so that's another question I can ask you is, what I want to get the value from 0.5 to 0.2 or the 2.0, I'm sorry, 2.0. How do I do this? What is the equation for that? Right, so I want to get this value right here. Well, simply what you do is you just divide this whole thing by 10, right? So in that case, every time when you get, the minimum value will be this, the maximum value will be this, right? Because you just divide the whole thing by 10. So that will also solve that problem, right? So in that case, this is the easy way of looking at it. So that's why I did not cover the last part on this chapter, because thinking like this is better, because then in that case you don't have to use that random function. It's in there. One thing I want to point out here, if you realize, especially for the computer science guys, if you're using a function rand in your program, right, rand, this will give you random numbers. Okay, so that's all right. But if you're using this random number in 2 or 3 computers at the same time, it will give you the same numbers. What does that mean? So this is a computer 1, this is a computer 2. Both computers get the same random number. But unfortunately, that's why it says even you consider as a random function, this function no longer random actually. It's just some fixed numbers for the given time it gives you, right? Unfortunately, you can test this on 2 machines if you want to use a random function and see. They'll give you the same number. So this is not actually random. There's another one called srand that gives you much more random capabilities. But any of these actually you don't consider random because it has some sequence, right? So it always has a sequence. You have to tell the computer to do something to calculate this. So it's not like your mind popping up values. It's just always there is some instructions on it, right? So that's why you can use a natural phenomenon like time. It's not natural, I mean human-made thing, but you can use that timer kind of things to calculate sometimes. Might work, but still you have opportunity. It's still open for anybody to come up with the actual random generator. There are no actual random generators still. I mean, we have flows in it. Okay, give it a try. I mean, that is something very interesting if you can come up with a pretty cool way of generating random numbers. Alright, so I will stop here, and then we'll talk about randomness next time. In that one, we'll talk about how to handle random numbers. Actually, the one I just talked about a minute ago, we're going to look at that and how we're going to apply that to an application. So that's what we're going to look at. Okay, all right.